Okay. Okay, the first thing I'm going to do is share screen, if I can find it. I have so many little chat buttons all over the place. I have now lost chat. There it is. Okay, so what we thought we'd do is share some of the latest problems we've been working on. And these are in what we call a feature for those of you who are new to these webinars. You can access the feature problems in a few different ways. The way I'm going to show you is the way where you can find all of the problems designed for students between 11 and 18. Students themselves can go to different buttons and find ones just for their age groups. So on the main NRICH webpage, if you go to secondary teachers, you can either click on the link up here or the little green blob, and that will take you to the secondary teacher page. And then there's always a box for latest feature. And then we have a link to the problems in this feature. Okay, Charlie, do you want to say a little bit about our theme for this feature?
Right, so it's all about reasoning, justification, and proof. And we know students find this, can find this quite tricky. So one of the things we've done with quite a few of the problems is offered students the opportunity to work on proof sorters. So we've got proofs with several stages, and we've muddled them all up and given and are challenging students to work out the right order in which to put the statements. And we think that this can be quite good preparation for when they have to carry out proofs of their own volition. The context is all number, and as an advanced organizer, we're going to have a similar feature being published in mid-February, which will also be about justification and proof, but the context is going to be geometrical. So it'll be similar in terms of reasoning, justification, proof. There'll be a few proof sorting activities as well. So we hope that this term, taking us all the way to Easter, will give students a really good experience of working on justification and proof, and how mathematicians present this in a rigorous way.
So some of these problems, as Charlie said, have got proof sorters. Some of them offer different methods for how you might prove these results. So there's a really good variety of problems, and we have probably more questions this time than we normally have in a feature. Okay, so the first problem we're going to look at today is 3 neighbours, and that's a problem which is useful for Key Stage through to Key Stage 3 students. You might also want to use it with some of your foundation Key Stage 4 students. And it's just about, just make this a bit bigger, about adding up 3 consecutive numbers. So the first thing I would like you to do, and in fact, I'll just hide that away again, is think of 3 consecutive numbers, add them together, and try it with a couple of sets, and then in the chat, put down what you notice. So you could add up 1 + 2 + 3 is 6, or 100, 101 + 102 is 303. So we'll just give you a few seconds to try adding up a few sets of consecutive numbers and write down what you notice about your results. So I tried this with my youngest child this morning, and what she noticed was that if you have 2 odd numbers and 1 even number, then you got an even answer. And if you had 2 even numbers and 1 odd number, you got an odd answer, which is correct, but wasn't what we were aiming for. Okay, we've got a few answers coming in. Got a few people saying multiple of 3. We've got some people who are going a little bit further than that and saying how the multiple relates to the numbers you've got. So students can try this with a few numbers and they can convince themselves that it's always a multiple of 3. And they might also convince themselves that it's always 3 times the middle one. But the trick is how to try and convince yourself that this always works. So we have 3 methods that we've got in little hide and reveal buttons. I think somebody is getting to my method already, which is brilliant. But as we say, this is a problem which is intended for Key Stage 2 through to Key Stage 3. So Liz's method, which I would term a bar model method, but I'm a secondary specialist, so I might not have the right terminology, involves a picture like this. Shall I keep going, Charlie, with the other methods?
Well, I wonder whether, I mean, so the question says, which is the question we're asking students, how does Liz's diagram help convince her that 3 consecutive numbers will always add up to a multiple of 3? So I don't know whether people want to, do we have time for people to write something in the chat, or do we want, actually we could ask Liz, since Liz is here.
Yes, of course we can.
Come on, Liz, tell us, is she paying attention?
I am paying attention, actually, and thank you for putting me on the spot. Yes, okay, I can say a little bit. So I think one of the key elements in my diagram are those dotted lines at the bottom. So you can see that those, if we look at the left-hand picture, you've got 3 consecutive numbers, and so those blocks are representing the fact that those consecutive numbers differ by 1. And then that green chunk, the green block, is moved from the left to the right to show that if we put that green block, that green one, onto the first of our consecutive numbers, we end up with 3 identical numbers. And because we know that consecutive numbers always differ by 1, we always know we're going to have that staircase pattern, if you like. And my dotted lines at the bottom are representing the fact that actually I've only drawn the very top part of the 3 consecutive numbers. They could be, those blocks could be any length. So I think that's the key, that because we know those blocks could be any length, this picture could represent any 3 consecutive numbers. And
the important thing, Liz, presumably, is that your diagram, the right-hand side of the diagram, shows that it adds up to 3 identical numbers, and 3 identical numbers added together will make a multiple of 3.
Yes.
And it also shows why it'll be 3 times the middle number.
Yeah.
That's great.
Yeah.
Okay, so shall we have a look at Charlie's method, and I'll try and explain. I'll give everybody a chance to read what we've written there. Do you want to enlarge it just a touch, Claire?
A bit even more, yep.
Just a little bit. There, perfect. So what I'm doing there is taking 3 consecutive numbers, or the first 3 consecutive numbers, and finding that they do add up to a multiple of 3. By adding 1 to each, I get the next set of 3 consecutive numbers. So from 1, 2, 3, I go to 2, 3, 4. And if I keep doing that, I'll then carry on and go to 3, 4, 5, 4, 5, 6, 5, 6. But every time I'm adding 1 to each, which is the same as adding 3 altogether. So if I've got a multiple of 3 already, and I keep adding 3s, I'm always going to end up with a multiple of 3. So I don't know what you all feel about this, but the reason we wanted Liz and Charlie's methods given some space here before we go to an algebraic method is to suggest that we can convince ourselves that something is always going to happen without necessarily resorting to algebra. And proof often has that sort of implicit assumption that you can't prove things unless you do resort to algebra. So perhaps there's a discussion to have here about whether we find Liz and Charlie's methods acceptable as proof or not. But let's give Claire a chance to.
Yeah, I was just about to say, I think Charlie's method is very suitable, especially if we stick some K's in it and turn it into proof by induction. But it is that sort of inductive idea which could be used with your sixth formers to start off that discussion. Okay, Claire's method is probably the one that you would be most familiar with as secondary teachers. This probably wouldn't be the way I'd do it. I would probably actually call the middle number n, so that I had n plus 1 and n minus 1, because that feels slightly more elegant to me. But since we're aiming this at key stage 2, key stage 3, keeping off the negative numbers is probably good, probably a wise plan at this point. The other thing that you can do is you can look at this method and look at Liz's method and show how the two are actually equivalent, which is quite a nice bridging between primary maths, where they do lots of bar models, and secondary maths, where we tend to go a bit more towards the algebra.
And Claire, if you factorize your last expression, the 3n plus 3, into 3 times n plus 1, you also show that your result is 3 times your middle number.
Yeah. Which
again links up to Liz's method.
Yeah, so there could also be a discussion about which of these proofs you think is the most convincing, which you think gives you the most insight into the problem, which I would say is possibly a different question. Which one do you think is the best, for how you want to define best? Okay, so at the bottom of this question, we've asked students, okay, what if you change it to add 5 consecutive numbers? What happens if you want to add 7 consecutive numbers? And they could use all 3 methods and try and convince for 5, or they could pick their favorite.
Or their least favorite, Claire.
Or their least favorite, yes. Yeah.
Because the problem sometimes is that we stick to our favorite method and then we don't gain confidence in. So I know some teachers will say, okay, well, if you used, for example, Claire's method to start with, okay, can you prove what happened with 5 consecutive numbers using one of the other 2 methods? And forces you, but I think asking them to use all 3 methods, since they're so beautifully explained, is a reasonable challenge.
Yes.
I haven't had a chance to look at what's been appearing on the chat. I'm slightly curious about what teachers think about the 3 different methods, and whether everyone feels that actually they deserve an equal status when it comes to calling them proofs. Shall we just give everyone 30 seconds to, if they want to say something?
Yes, I've had a message that's come direct through to me rather than to everybody about proving for odd and for even numbers. That's where we're going to go next. So one thing you might notice about all of these is that we added 3 consecutive numbers, 5 consecutive numbers, 7 consecutive numbers. So there's a reason why this problem concentrates on odd numbers.
And D. Segura says, I like the idea of trying with 5 consecutive numbers, 7. And yes, it feels like you can adapt the 3 methods very easily. And what we like about that is to show that the generality of these methods, actually, if I had 101 consecutive numbers, I could start picturing Liz's method and taking the 51st column and leaving that, and then swapping things around and so
on. Somebody said the second method doesn't establish it's a multiple of 3. I think it does establish it's a multiple of 3. It doesn't necessarily establish that it's the middle one without a bit more tweaking. So with the second method, you can show that if you add together the first 3 numbers, Actually, I'll just see if I can annotate. I will have to just try and find the button. Sure. Okay, so with the first method, we can do 1 + 2 + 3 = 6. So we know that it works for the first 3 consecutive numbers. Then if we increase each of these by 1, then we'll still get 3 consecutive numbers. And because the increase is equal to 3, it means that we've gone from one multiple of 3 to the next multiple of 3. So it's still a multiple of 3. We could do it algebraically and assume that it's true for the 3 numbers that start with K and then look at the next 3 numbers. But it's that same idea. Every time you move your 3 consecutive numbers up 1 step, each number increases by 1, so you're still on a multiple of 3. So I would say that one does constitute a proof, but conceptually it's a little bit harder. I hope that answers that question. No problem at all. Okay, let's get rid of those.
I think Chris Shaw deserves a gold medal being on a webinar while in the car on a school run. That's quite a commitment to. I hope Chris is not driving.
Right, yeah, that's what went through my mind as well.
Okay, so we then have another problem. So we're not going to have a chance to show you all the problems because we want to go in a bit of detail. But the one that follows on nicely from 3 Neighbours is what does it all add up to? Because it talks about even numbers. So before clicking on, oops, I was going to suggest, Claire, that we ask everybody. So we've sort of addressed what happens when you have 3 consecutive numbers, and perhaps you can imagine what happens when you have 5 and 7 and 9 and 101 consecutive numbers. What does it all add up to is a nice problem to carry on with. And that starts by asking what happens when you have 4 consecutive numbers. So what we'd like you to do is add 4 consecutive numbers and just type into the chat what total you get. And once we've got some totals, we can then start making a conjecture about what they all have in common. So we've got a 22, a 26, a 90, 10.
Yep, I like 10. 10's a good one.
Why is 10 a good one, Claire?
It's the smallest one.
Okay.
Someone's done the first 3. Yep.
So Jay Dixon, who's got 10, 14, 18, in a way, that's not a surprise, is it? Because if you think about Charlie's method for the first problem, where he was adding 1 to each number. So if you've got a total of 10 and you add 1 to each of the numbers, you're going to get the next 4 consecutive numbers. And so the totals are going to go up in 4s. So what do all these numbers have in common is, how could you describe, is 100, I mean, they're all even, is 100 going to be in this list? Yep. Is 100, which even numbers, which?
Would 24 be possible?
Will 2024 be possible?
Will 2024 be possible?
Yeah, you're being far too.
Yeah, I'm being too nice.
He's nice to everybody. Will 1 million be on this list? I don't agree with 1,024 being there. So
No.
can somebody perhaps help to explain why 1,024 won't be on the list?
I was just getting a blank page ready in case I need it.
I think
Oh, so there's some good thoughts going on here. Okay. So have we decided whether 1024 is possible or not?
well, some people are saying that when you divide 1,024 by four. Okay,
let's have a look at this question in more detail, because this is becoming quite fun. I'm allowed to go for my method.
Well, can we just write some of the numbers that we got, Claire, to start with? Because this is not a proof, but we had 10, we had 14, we had 18.
Yeah, I just need to get my pen up. And now I've moved that in the wrong way.
I can use my visualizer otherwise.
No, I'm there. So 10, 14, 18. Yep.
So by just thinking about it in terms of how Charlie was thinking about the previous problem, I think we could carry on that list with 22, 26, 30.
That'll do.
And I can see that they're all even numbers, but I can see that 12, 16, 20, 24, 28 didn't appear. So it looks like the multiples of 4 don't appear, but the even numbers which are not multiples of 4 do appear. And of course, that doesn't, I mean, we're trying to distinguish between what we see and a proof here. So this is where an algebraic proof is going to be really helpful. And yes, the 1,024 is going to be a multiple of 4. So that's why I didn't think it appeared. So here, Liz's method might not be quite as easy. Well,
actually,
method.
Thinking about this, somebody has mentioned in the chat that it's always 4 times the average of the middle 2.
Yes.
So if you think about having 4 numbers, I'm just going to blob them. And I think somebody said that it's always 4 times the average of those 2. It was either that or it was 2 times the sum of those 2, but I think that was what somebody said. So if that was going to be true, then if we were going to have a sum of 1024, then this number here is going to have to be a quarter of 1024, which is 256. So then 256 is going to have to be halfway between 2 consecutive integers, which gives us a bit of a problem.
But also, you can think about those 2 middle numbers. One's got to be even and one's got to be odd because they're consecutive numbers. Mm-hmm. So they're going to add up to they're going to add up to an odd total. And when you average those 2 numbers, you're going to get something and a half.
Yeah.
You're not going to get a whole number when you average 2 consecutive numbers.
Yeah. So there's lots of different ways of thinking about the same problem and convincing yourself that you are Right. Let's just find the actual problem again.
I was just wondering, Claire,
Yep.
if we did the Claire's method with the algebra,
Yep.
I mean, which is reasonably straightforward with n plus 1, n plus 2, n plus 3, then actually Liz's method, in a way, can be used as a diagrammatic representation of the same thing.
Yeah.
So we're going to get 4n plus 6.
I'm not very good at drawing.
Actually, I think you're doing remarkably well, Claire.
Yeah.
So this gives you 4n plus 6, your algebra, which is the same as 4n plus 4. Can you, yeah.
Okay, so if I'm just going to try and change colors.
Can you factorize that to 4n plus 4 plus another 2?
Yep.
No, oh, yeah, simplify to 4n plus 4 plus another 2. And then can you express that as 4 lots of n plus 1?
Yep.
Plus 2.
So one of the things when doing this sort of problem, I would probably write it out like this. I would explain to my students that those brackets are not needed, but they just help you to isolate, to show that those are different terms in your sequence.
And now, Claire, if we just shade the very bottom little square, that one there, and add it at the top, you can then see that you've got 4 lots of n plus 1. And then you still have 2 little squares left.
Yeah.
And it's really nice being able to show a diagrammatic representation of the algebra. I don't think students often realize that they can do this. And I quite like, we started with the diagrams in the original problem and then went to the algebra. But here, being able to show that you can represent diagrammatically what's happening algebraically is quite nice.
Okay, shall I go back to the NRICH side?
Yeah, sorry.
That's right. No. I may have to just get rid of some annotations. I've made a bit of a mess of the page. There we go. Okay, so we'll go back to the problem. So we've already discussed a lot of this already. I have got one little blob left. But we've also created, as Charlie said, proof sorters. And this is our first proof sorter that we're going to show you today. So it's trying to show that the sum of 4 consecutive numbers is always an even number and is not a multiple of 4. So we'd like to give you a few minutes to have a play with this. So if you'd like to go to the problem, if you have another device, I think Liz posted the direct link in the chat, but we can do it again. And what you can do with these is you can move these about and put them into a new order. And then when you think you've got it in an order that you like, you can press submit. So we'll give you about how long, Charlie? 2 minutes?
Well, we're not very much time because I've given it away by forgetting that we were going to give everybody a chance to do this. And
yes, true.
I've given away the answer to this, but it might be good just for everyone to just get a chance to play with the proof sorter. And then we're going to give them some more difficult proof sorters to do in a second. So apologies. This was planned differently and it's Charlie not sticking to the plan here.
That's fine. Well, what I'll do, whilst you're having the play, I'll try and sort this out as well to what I think it is. And one of the great things about these proof sorters is it models what I would consider to be a rigorous proof. So things like let the first number be is a very sort of mathematically way of starting a proof. And it gets students used to that idea.
Yeah, that's the kind of the rigor that I was talking about earlier, that for students who are not used to setting out their work in this way, working with these statements which model how mathematicians set out proofs, hopefully will induct them into how the mathematical community normally goes about presenting convincing arguments.
No, somebody's proof filter is not interactive. Ah. If anyone else is having a problem not being able to move, Liz is on the case. I think I said a minute ago that the first number was A, was the first statement. I think I've changed my mind. I think that's probably the second one. Yeah.
I think your penultimate, wait a minute.
Yes,
okay.
I had the other therefore at the end, but we have, so quite often if there's a therefore, that probably goes at the end. But in this case, we have two therefores. Okay, I'm quite happy with that. So I'm going to try and click submit. And if you get them in a correct order, hopefully you'll get a tick. If you have them in a slightly illogical order, you will get a try again.
Somebody has posted that they're going to try and do it by hand. Yep. So could you go to the teacher's resources? Mm-hmm. Because what we've done is we've put a link to printable cards. So if you want your students to have if your students don't have access to Wi-Fi or computers or whatever, you might decide you'd quite like to get students working on this in a classroom, maybe in pairs, and you might give them this sheet to cut up and organize. And then we've labeled each row from A to G in this case, so that then you can discuss what the right order is. So for all the problems that have got proof sorters, in the teacher's resources, we've got a printable version with the same statements.
Yeah, so to find the teacher resources, there's always on the side of the problem a link to teacher resources, and you can just go to there. In a similar way to Three Neighbours, we've also got a few extensions. So we've asked them about 5 consecutive numbers in case they haven't seen Three Neighbours yet. But then we've also asked them to think about 6 consecutive numbers. And then there's a couple of more challenging extensions at the end. I've just remembered the thing that I was meant to do on this problem and I haven't done yet, which is to link to the next problem. So we're going to look at a third problem today as well, which is also about consecutive numbers. And if I head back to the feature, the next problem we're going to look at is called impossible sums. Okay, so Charlie, do you want to say anything particular about this one? And should I have shown the problem or should I have hidden it for a little bit longer?
No. Okay, so with 3 consecutive numbers, we found that we always got multiples of 3, and with 4 consecutive numbers, we got multiples. Sorry, we always got 2 more than multiples of 4. I imagine you can guess at 5 consecutive numbers, you get multiples of 5. And I think it possibly said in the previous problem that if you have 6 consecutive numbers, you get 3 more than multiples of 6, and so on. And one question that arises is, well, can we write all the numbers as a sum of consecutive numbers? So
So if you've been working on what does it all add up to, we saw that 24 can't be written as a sum of 4 consecutive numbers. But if you remembered what we did on 3 neighbours, 24 is a multiple of 3. Therefore, we can write it as a consecutive sum. It's 7 plus 8 plus 9.
Yeah, because it's 3 times the middle number.
Yeah.
In case you were wondering how Claire did that so quickly. And likewise, 25 is 5 times 5. So if I put 5 in the middle and I put 4 and 6 on either side, and then 3 and 7, I'm going to get 25 as well. 26 is 2 more than a multiple of 4, so I'm going to be able to write 26 as 2 13s, and 13 is 6 plus 7. So if I put 6 and 7 in the middle.
Yep. 28 is, again, that's multiple of 4, but it's also a multiple of 7. So we think we can write that as a sum of 7 consecutive numbers. So what I'd like you to do for just a few minutes is have a think about the numbers 1 to 20 and see if there are any numbers there which you don't think you can write as a sum of consecutive numbers. I'll give you a starter for free. We're talking about more than 1 consecutive number, and we're talking about positive numbers, and somebody's already said it, definitely not 1. So 1 is an example.
So just to clarify, Claire's asking which numbers between 1 and 20 cannot be written as a sum of consecutive numbers.
Somebody said not 2 either. I think I agree with that. Three equals 1 plus 2, so 3 is a possible. We're only looking at positive numbers. I think, have we said that anywhere in this? We probably ought to.
So D. Segura has said even numbers, but we can write 6 as a sum of 3 consecutive numbers, 1 plus 2 plus 3. So
that's a very common
even number that can be done.
Yeah, but that's a very common thing that students might say once they've worked out that 2 can't be done and 4 can't be done. They might at that point say all even numbers.
Claire, do you mind if I share my screen for a minute?
No, go for it. I'll stop sharing. I'll try and stop sharing. Why did that not work? There you go. I've got some very good ideas coming on chat. Oh, we've got 14 that's cropped up. 14 is a nice one because that's 2 more than a multiple of 4. So it can be written as 4 numbers. You might think it should also be able to be written as a sum of 7 numbers because it's a multiple of 7. So I'll come back to that one in a minute.
So I'm going to try and make life a little bit easier for everybody. I've listed all the numbers from 1 to 20. And in the first problem, we agreed that all multiples of 3 could be written as 3 consecutive numbers. So I know I can do 3, 6, 9, 12, 15, and 18. We didn't do multiples of 5, but you can imagine adapting Liz's method and finding that 5 consecutive numbers will also add up to multiples of 5. So we can do 5, 10, we've already got 15, and 20.
No, we're not allowing 0 to
Yes.
the person that asked.
And we haven't talked about 2 consecutive numbers, but I know that if I add 2 consecutive numbers, I'll have an odd total. So I think I can do 7 by adding 3 and 4, 11 by 5 and 6, 13 by 6 and 7, 17 with 8 and 9.
And 19.
And 19 with 9 and 10. Thank you, Claire.
Okay. Somebody's already demonstrated how to do 14.
Which is 2 more than a multiple of 4. So we know that we can do that with 4 consecutive numbers. So I'm thinking it's 2 7. So I've got the 3 and the 4 in the middle, and then the 2 and the 5 on the other side. So 2 plus 3 plus 4 plus 5. And lo and behold, I'm left with what a lot of people have been suggesting, which is that we can't do powers of 2. So unless somebody can show me how to do 1, 2, 4, 8, or 16, this seems like quite a nice way of organizing our work and convince ourselves that, well, partially convince ourselves. We'll move on to how do we convince ourselves for sure. Okay, I've stopped sharing, Claire.
Okay, I'll share back again. If we can find the right screen, otherwise we'll get an infinite display. So there's sort of 2 parts of this question. So we are fairly convinced now that all powers of 2 cannot be written in this way. And we've actually got 3 different proofs for how you can do that. But there's also the alternate question, which is, can anything which isn't a power of 2 be written as a consecutive sum? And those are 2 very different questions. And students might not always be aware of the need to prove things in 2 directions. So it's a good example of that sort of statement and being very careful with logic. We've got 3 proofs here. We've probably got enough time to let you have 5 minutes to play on one of them. I didn't write down what the 3 proofs involved. Charlie, have you got those written down?
Yes. No, I don't have it written down, but I thought the first proof involved summing a sequence. The second one involved thinking about means and median averages.
Yes.
And the third one was thinking about triangle numbers.
Yeah.
So if you've got a preference, I mean, you might have time. We've still got quite a lot of time.
If you've got a preference, if you want to avoid a lot of algebra, proof 2 probably has the least algebra. If you really like triangular numbers, then proof 3 is very nice. If you like arithmetic progressions and you want to see how you might use some of the A-level work to answer this question, you might like proof 1. But what we'd like to do is give you 5 minutes to have a play with one of those 3 proofs and see how you get on.
Yeah, and we're hoping that a few people will look at proof 1, and at least a few people will look at proof 2, and at least a few people will look at proof 3. So if you don't have any preference for which method, we thought that if your birthday was between January and April, you could have a go at proof 1 initially. If your birthday was between May and August, you could have a look at proof 2. And if your birthday was between September and December, you could have a look at proof 3. And while you're working on these proofs, I suppose what we're interested in is 2 things. One is to be thinking about your students and where might they have some difficulties? How do you prepare your students for engaging in these proofs? Because these 3 proofs are slightly more difficult than the ones we've looked at so far. So where might the stumbling blocks be? But also, because we've only recently published this, if you feel that we've written something that's not completely clear, it's not too late for us to tweak any of these proofs. So we're sort of using you as guinea pigs as well as offering you the webinar. If there's anything you feel we could do to improve them, it is possible for us to do that. But in a way, the important thing really is to be thinking about each of the three proofs, which we'll talk about them in a minute. Where might the stumbling blocks be? Okay, and then if we've got time, we'll look at the proof of the converse. But initially, we'll just look at those first three proofs. And again, if your interactive proof sorter is not working, you can just click on the proofs and you'll find that there are printable versions of this. Mind you, I suppose, yes.
We might not have time to print them off.
No. And of course, the proof sorter will have even if you can't move them around, yeah, you'll be able to see what the statements are. Okay, I'm going to be quiet for a few minutes.
I'm just going to address an issue about 3. We can have a sum of 2 consecutive numbers. So 3 is fine because we can have 1 plus 2 equals 3. So 2 consecutive numbers are also allowed. So I'm just having to stop sharing for a second whilst I have a look at proof 3. Ah, yes, that's a very good point. In proof 2 and proof 3, we have fixed some of the statements because some of these proofs are quite tricky and there are some bits we wanted in a particular place. So the ones that are in a different colour, you can't move. We should have mentioned that bit.
Yes, I think that's where you say something about if it's odd this, and then later on if it's even this, and it makes no difference to the proof whether you start with one or the other.
It makes it slightly easier for us to
do the odd.
Well, it makes it slightly easier for us to be able to tell whether it's correct or not, rather than trying to put in all the different possibilities.
Yes, but also surprisingly, the proof is easier. It's easier to start thinking if there's an odd number.
So just to demonstrate for those people who are looking at proof 1, the blue statements can move.
We can't see your screen. Oh. I can see Microsoft trying to encourage you to save your work.
Oh, darn, I probably shared the wrong screen. Try that. That might look better.
It does look better.
Yeah. So the blue ones can move. The brown ones are fixed. Proof 1 aimed at which key stage? Well, proof 1, it does have arithmetic sequences in it, so you could argue it is key stage 5. However, I think it's accessible to key stage 4 as well, because we don't assume that they know anything about the sum of arithmetic sequences. We have basically run through a proof of how you find that sum for them.
Yes, sort of from first principles,
yeah,
rather than using the formula.
That's not to say it's easy. But...
Except that it's a lot easier than if we didn't have the statements. So then, when I was first given this problem and just left to think about it, it was quite hard having the statements and asked to reorganize them. It seems to us makes the proofs much more accessible.
Okay, we've got about 7 minutes left, and I did want to say a little bit about 14 and in connection with the proof of the converse. So do feel free to keep playing whilst I am talking about 14.
I've got the 3 proofs solved on my screen.
Do you want to do that first?
Do you want me to share that? Is that,
yeah,
do
that's fine.
People want to see what these things look like completed? I don't know.
Somebody said, oh, why is it not possible to submit proof 1? It should be. If you don't get a submit button, it might be that you haven't quite lined up the boxes exactly.
Yes. Okay, so I'm going to share my screen quickly, just so that if
Okay, Charlie.
I think so. Can you see that?
Yeah, it's slightly small, but that's
okay. No,
well, you can't make it that much bigger because you can't scroll up and down.
Okay, so this is proof sorter 1, where we consider the consecutive numbers, we write them down as the sum of numbers in ascending order and then in descending order. And then we imagine adding top to bottom, we get twice the sum. And then there's an argument here about what happens if k is even and when k is odd. So I'm not going to spend too long on it because you may want to work on it yourselves. Here's the second one. And it talks about the sum of the numbers being equal to the mean of the numbers multiplied by n. And since the numbers are evenly spread out, the mean is equal to the median. And then
I think that's the one that probably has the least maths in it, but has a couple of very bright ideas to make it work.
Yes, it was definitely, it wasn't a solution that I came up with, but it was a solution that a student came up with when this problem was live on the site without the proof sorter, and we really liked it. So yeah, so if n is odd, and then what happens if n is even? Therefore, whether n is even or n is odd, we're not going to be able to express powers of 2 as a sum of consecutive numbers. And then the third one talks about triangle numbers, and consecutive numbers could be thought of as the difference between 2 triangular numbers. So there's a bit more algebra here.
There's slightly tricky factorization.
Yes.
But that's probably my favorite one.
It is nice. It is nice. But yes. But again, it's quite nice because we know that a triangle number is the sum, the fifth triangle number is the sum of the first 5 consecutive numbers. But to think about, well, what happens if you add the numbers from 6 to 10, to think of it as the 10th triangle number minus whatever it was I said, minus the 5th triangle number is quite nice.
Okay, just before we finish this problem, I wanted to talk a little bit about the converse. And I just wanted to show you the idea that the proof of the converse is based on. So when we were talking about consecutive numbers before, somebody said that 14 can be written as 2 plus 3 plus 4 plus 5.
Yes.
Now 14 is a multiple of 7. In fact, 14 is the same as 7 times 2. So you might think that you should be able to write it as the sum of 7 consecutive numbers with 2 in the middle. And it actually turns out that this is correct. So if you write it as 4 consecutive numbers centered around 2, and so I'm talking through this quite quickly at the moment.
Do you mean 7 consecutive numbers?
What did I say? 14.
4.
4. So you can think of it as being 7 consecutive numbers centered around 2. Then you end up with some negative numbers, but it turns out that the negative numbers cancel out some of the positive numbers. And that's how you can end up with your sum of 4. And that idea is what you use for the converse. So for any number which has an odd factor, you can write it in a list of that number of numbers, whatever the odd factor was. I've got too many numbers to make sense here. And then you can cross off the ones that are negative, and you always end up with a sum. So I would say do have a look at the proof of the converse as well, because it is quite a fun proof. It's conceptually a little bit tricky, but it is nice. Okay.
Go back to the teacher's page so that we can go back to where the feature is, the secondary teacher's page.
Yep.
So the green lozenge.
Okay, I'm trying is, it's just been a bit slow.
Because somebody asked for the link to this problem earlier. So the easiest way to get to these problems is to go to the green lozenge at the top of the page, which has got secondary teachers, and then the latest feature there takes you to all the problems that we've been looking at. And you will find many more that we haven't had a chance to talk about. But there was a couple of things we wanted to mention before saying goodbye. At the top of this list, we have put a link to some articles about proof. So within the Millennium Maths project sit 2 different projects, Plus, which is a sort of sister organization, and NRICH. And Plus writes for a slightly adult audience, or 16 plus audience, so 6th formers, university students, and beyond. And they have collected for us a package of articles all about proofs, and they've got slightly different sections. What are they and why do we need them? They've got some nice proofs. They've got something, I can't remember what the other,
elusive
proofs. And you may have students, I mean, you may yourselves be interested in these articles, but you may also have students who you may want to direct to these articles. We've also put a link to this in the 16 plus students, haven't we? The post in the purple lozenge.
Oh yeah, so I'm already there. So post 16, latest feature. Yeah.
That so also has a link to the articles.
Yeah.
And before Claire says goodbye, the other thing that I wanted to show you is if Claire scrolls right to the bottom, there is a contact us link with an email address that, so I think secondary comes to me and post 16 goes to Claire. If any of you have got favorite proofs that you think would lend themselves to a proof sorter, do feel free to email us with suggestions. And we've got the sort of the structure there set up to produce proof sorters. So if you think, if you've got some favorite proof sorting activities that you've used in your classrooms and you think are worth sharing, do email them to us. Okay, apart from that, I'm assuming Liz is going to also say something about evaluations, or maybe you are, Claire, but I'll say goodbye now.
Thank you, Charlie. Thank you, Claire. I'm more than happy to do a final finish up. Claire, would you mind stopping sharing so I can just share? Thank you very much. Just to round things off, I'm just going to go through a few admin points with you. If you don't already, do consider following us on Twitter, because that's how you'll find out about further events like this. And you'll also you'll also find out about everything that goes on. The handle there you've got there, the NRICH Live Twitter handle. If you wanted to tweet about what we're doing, about what you've been doing as a result of this webinar, we'd be delighted to hear from you. The other way to hear about what we do, if you're not on Twitter, is via our email newsletter, and you can sign up there. Charlie and Claire have given you a whistle-stop tour of the current feature, but if you're interested more generally in the secondary resources, that would be the page for you to have a look at. You'll find there everything secondary on NRICH that's linked to the mathematics national curriculum here in England. Charlie was very clear about how you find the current feature that we've been looking at, and there's a link to all the previous features that we have created. You'll also find that link on the secondary teacher homepage. One of the other things that Claire is involved in is STEP, which is one of the examinations that's required for entry into some universities. And if that is of use to you, then please do take a look at our STEP resources. We will put a recording of this event up on the NRICH site, and you will be able to find it there, as well as a PDF of these slides in case you haven't got around to scribbling links down. We'll hope to have that ready by the end of the day tomorrow, but if not, it will certainly be ready by the beginning of next week. We're very grateful to Trinity College here in Cambridge for funding these webinars. And we really would like to continue to make them better and better. So please give us your feedback. I've posted the link directly into the chat as well, and perhaps Claire has, I haven't been paying attention, but we'd be very grateful for your feedback. Finally, we have been super organised, and we already have the booking details ready for our next secondary teacher webinar, which will take place on the 1st of March. So do sign up for that right away, should you wish. We hope that you have enjoyed this afternoon's webinar, that you've found resources and ideas to take away into your classrooms straight away. Thank you for your enthusiastic participation via the chat, because that does make our lives a lot easier. Thank you very much, and have a lovely rest of your evening. Goodbye.